Okay. So you feel that optimization is difficult, that's normal. Many people feel the same. So we aim to simplify these expressions and try to map this subprimum directly to the power applications. So we can do that by what we call as singular value decomposition. So we are trying to decompose the MIMO channel matrix, make it an element with a unitary element, make it another element with another unitary matrix, and in the middle we have an element that represents a diagonal matrix. So once we have a diagonal matrix, we can convert the MIMO channel, the one having the NR by NP matrix, into a parallel channel, which is much simpler. Okay, so remember we have this channel model, then we have the singular value decompositions, we have H equal to U. So this is a standard singular value decompositions. You can invoke this in MATLAB. I will show you later if you are not familiar with this representations. So we can represent this channel by using three different matrices. We have U. U is a unitary matrix. The capital lambda, right? I'm not sure. What does it call in Greek? Lambda, capital lambda. And then we have the V conjugate. V is another unitary matrix. And then that capital lambda is a rectangular matrix. So in the case that H is a square, is a square matrix. So the good thing about unitary matrices is that if you multiply that matrices with any, let's say, random factor, the distribution is maintained. So you do not change the distributions by multiplying that with the unitary matrix. And then we have this capital lambda, which is a rectangular matrix with non-negative real numbers, so it is real, not complex, in diagonal elements and zeros in off-diagonal elements. So basically, you will have like a matrix that looks like, like A, B, and the rest is zero. So it's very simple representations of a matrix. So we let that n is the minimum of NT and R, because everything later will relate to that. And the diagonal elements of this capital lambda is what we call as the singular values of H. Okay? We have y equal to h x plus z, and then we have h decomposed into three matrices: u, v, x plus z. So if we multiply this y with the conjugate of u, so let's define that y tilde as the conjugate of u multiplied by y. How do I have this? Okay. Y tilde u, y. So we multiply the whole thing with the conjugate of u. So this means that u conjugate multiplied by u is identity matrix. So identity matrix is resolved. It is absorbed by the rest of the thing. So we just simply have capital lambda p conjugate x plus u conjugate. The reasons why u disappear because we multiply this u with the conjugate of u. So unitary matrix, if you multiply itself with its conjugate, will give the identity matrix. So identity matrix is like 1 in scalar. So 1 multiplied by anything is anything, right? Okay. And then remember that our objective is to convert the matrix into parallel channels, and the next step is simply defining this as X conjugate. So V conjugate X is equal to X tilde. So overall here we can transform these equations into Y tilde equal to capital lambda plus X tilde plus Z tilde, where Z tilde is given by X. So with these representations, the good thing is lambda is capital lambda is like a diagonal matrix, right? So you have a diagonal matrix, like let's say we have the singular value of lambda 1, lambda 2. This is just an example, so I should not put an equation here. So example. Then you have x1 tilde, x2 tilde, plus x1 tilde, x2 tilde. So if you do the usual matrix multiplications, you will have here lambda 1 x1 plus z1 tilde, and then the second one is lambda 2 x2 tilde plus z2 tilde. Okay? And that will be y1, y2. So now we have y1, which depends only on lambda 1, x1, z1, y2, lambda 2, x2, z2. So in a way we have parallel channel, right? So instead of having a channel that looks like this, where this represents MIMO channel matrix, now we have a channel that looks like this. Right? One is defined by lambda 1, the other one is defined by lambda 2. Okay, so as I mentioned earlier, that unitary transformations preserve the distributions of noise. Unitary transformations also preserve the energy of the signal. So from the perspective of the channel capacity, nothing is affected by doing this transformation. Okay, so how does it look like? So we want to see things that looks like a parallel channel, right? So we can start with X tilde, because we want to see things that represent this parallel shape. So what is X tilde? X tilde related to X. So X tilde is equal to V conjugate X, right? So in this case, you can also write that X is equal to V tilde. Because you multiply this by V conjugate is I, right? Identity matrix, right? So that's why we have V there, and we have X. And everything here is actually the original MIMO channel matrix, but you can see it as a parallel channel. So we have V, we have the eigenvalues, we have the U. And at the receiver, we have what we have. So we have Y, so what we want to see is Y tilde. So Y tilde is equal to U conjugate, complex conjugate, multiplied by Y. Okay. So because it's parallel channels, the capacity is simply the sum of each of the branch. So you sum over all the branches, And then you have the typical like single input, single output Shannon capacity expressions. Simply sum them up together. Okay, so, and then the trick here is that because we want to optimize the Q, right? Remember, we want to optimize the Q. So the way we translate this problem is that we optimize that Q by choosing an appropriate power. So we are doing power optimizations for these capacity expressions. Then that result of the optimization is given by what we call it as a water filling allocation. So water filling, okay. The name there exists for a reason. It's not simply like random people just call it random stuff like water filling. So the reason exists for that. Suppose that we have a